Good morning. Let's start today's lecture. Today's lecture divided into natural part. First part is the ending of the last previous lecture and devoted to the tangent to the conics. And now we consider the tangent to the hyperbola. The main theorem is the following. Tangent to the hyperbola, which is defined by the equations, by the canonical equation, at any point P1 with coordinates x1, y1, has the equation which is the same form as in the case of the ellipse and parabola, and this form is the following. The first coordinates x1 times x divided a square minus y1 times y divided b square is equal 1. Is the same form. And let's prove this assertion. Let's consider the hyperbola. Let's have the main rectangle of the hyperbola and asymptotes, and the hyperbola has the following form. We have foci f and f1, f prime, maybe f and f prime, with coordinates of first focus C0 and coordinates of the second focus minus C0. A and B define the size of basic rectangular, and we have the following formula: c square is equal a square plus b square. The ratio c to a is equal e eccentricity, and we have also directrices which defined by the equation x is equal ratio a e, x is equal minus ratio a e. And let's consider the point P1 with coordinates x1, y1, and other point Q with coordinates x1 plus h, y1 plus k. And coordinates of this point are devoted to basic equation of hyperbola. And the ratio k to h is the slope of the section of the slope of our section, and in the limit when h goes to 0 and k goes to 0, we obtain the slope of our tangent. The slope of our tangent. And the equation of our tangent is following: y minus y1 is equal m times x minus x1. And let's calculate the slope m. First of all, easy to see that slope is a ratio of the differences k and h. And we know that the coordinates of q and coordinates of p1 are satisfied the basic equation of the parabola, or of the hyperbola. X squared divided a squared minus y squared divided b squared is equal 1. And we can write this equation in the form b squared x squared minus a squared times y squared is equal product a squared b squared. And we obtain the two following equality. First of all, equality for coordinates of point P1, and we obtain the equality b squared times x1 square minus a square y1 square is equal a square b square. And other equality b square times x1 plus h, the second equality for coordinates of the point q, h square minus a square times y square plus k square is equal a square b square. And we can transform to equality and subtract for the second equality first equality. And after subtraction, we obtain, let's obtain from the second equality first equality. And we obtain the following. Oh, okay. Okay, good morning. I briefly repeat the previous reasoning. We consider the tangent to hyperbola, the heading of the previous lecture. The main theorem, which I try to prove, is following. Tangent to the hyperbola, which is defined by this canonical equation at any point P1 with coordinates x1 or y1 is defined by the following equation. This equation is the same as the case of the ellipse and has the following form: x1 times x divided a square minus y1 times y divided b square is equal 1. That's tangent, the equation of tangent to the hyperbola. If we compare this equation with equation of the hyperbola, we can that we change one of the variable in the equations of the hyperbola by the fixed point P1, this exactly a point in which we consider the tangents to the hyperbola, and change one of the variable by the coordinates of this point. And in such way, we obtain the equation of tangent to the hyperbola. As the same form as the case of the ellipse and parabola, and we have the same form for the tangent to the any conics. And proof of this theorem. Let's consider the hyperbola. We have the basic rectangle of the hyperbola, which has the following size. One size have twice a, the other size twice b. We have the asymptotes of hyperbola to foci f and f prime with coordinates c0 minus c0, where c is defined as the sum c squared is equal a squared plus b squared, and the ratio c and a is equal e eccentricity of the hyperbola. And as the previous cases, let's consider 2 points. Let's consider 2 points. Let's consider 2 points on the hyperbola. One point P1, be the fixed point, and other point Q. Q can goes to P1, and when Q goes to P1, the second which pass through to this point tends to the position of tangent. In the limiting case, when Q1 goes to P1, we obtain the tangent. The section, the second which passes through this point tends to the tangent. And the ratio of difference between second coordinate to difference to the first coordinate, this ratio is the slope of the second, and the slope tends to the slope of the tangent. And we obtain that the slope of tangent m is equal limit the ratio k to h, when h and k tends to zero. We have the general form of the straight line which passes through point with coordinates x0, y0, if this straight line has the slope which equal m. The equation of the straight line is equal difference y minus y1 is equal m times x minus x1. And our goal to obtain the exact value for m. And from this equation we obtain in our case the equation of the tangent which passes through point P1 x. We change y0 x0 on y1 x1. General form of equation of the straight line. In our case, we obtain the equation of our tangent. And we calculate the exact value for m as using this formula. And we have 2 points, Q1 and Q, which lies on our hyperbola. And then the coordinates of this point are satisfied to the equation of hyperbola. By definition, if we have any point which lies on the curve, by definition, the coordinates of this point satisfy the equation of our curve. by definition, the equation of the curve defined the set of points which lies on our curve, definition of equation of the curve. And by definition, we obtain that coordinates of point P1 satisfy the equation of hyperbola. We rewrite this equation in the following form. We multiply left and right side on product a square and b square and obtain this form. And we have two equality, one for coordinates of point P1 and other equation for coordinates of the point Q. And after them, we subtract from second equation first equation, from the second equality first equality. And we obtain the following difference. In this case, we have square of the sum. So, to this variable, and by the formula for the square of the sum, we obtain that we have the square of the first term, twice product of this term, and the square of the second term. And in this case, we have the square of the first term, and the difference is equal b square times 2x1 h plus h square minus a square twice y1k plus k square is equal 0. And we can rewrite the last equality in the following form. B square b square h times 2x1 plus h is equal a square k times 2y1 plus k. And from last equality, we obtain that the ratio k to h is equal the ratio k to h is equal the ratio 2x1 plus h to y1 plus k. We obtain the exact expression for the slope of the second. And in the limit, when h goes to 0, k goes to 0, this expression, I'm sorry, b square and a square. this expression goes to the ratio b square x1 a square y1, and we obtain exact value for the slope. The slope of our tangent is equal b square x1 divided a square y1. And if we substitute this value to the equation of the straight line, we obtain the equation of the tangent, the exact value of equation, for equation for the tangent to the hyperbola. We obtain the following formula: y minus y1 is equal the product m, which is equal the ratio b square x1 square and a square y1 square times x minus x1. We can write the last equality in the following form: a square times y1 square times y minus y1 is equal b square x1 square x minus x1 square. And after the simple transformation, we obtain the following form: a square. Oh, I'm sorry. Without square. Excuse me. Without square. We obtain the following equality: a square times y1 y minus a square y1 square is equal b square x1 x minus b square x1 square. The last equality we can write in the following form. Let's shift it from the left side. The term a square y1 y in the right side, and we obtain the following equality: b square x1 minus minus a square y1 is equal b square x1 square minus a square y square. Easy to see. The right side is equal a square b square, because the coordinates of the point P1 satisfy the equality to the hyperbola, and the left side is equal exactly this one, and we obtain the following equation: b square x1 minus a square y1 is equal a square b square. If we divide left and right side by the a square b square, we obtain exactly this equation. x1x divided a square x1 minus y1y divided b square is equal 1. Is exactly the equation which we try to prove, because the multiplication of the numbers is commutative. We can change the order. And this one is equal to this one. And we obtain the exact formula for the tangent straight line to the hyperbola. Maybe any question? Okay. We can consider.
Yes. On the left, b squared x1 squared minus a squared y1. There shouldn't be x1 squared, right?
We use the fact
because y. Okay. Sorry. Continue.
We use the fact that the point P1 lies on our curve, and therefore satisfied the equation of the straight line. But this equality is exactly equation for our hyperbola. This one and this one are equivalent. Okay?
Okay, so there y1 should be squared and x1 should be squared and y1 not, right?
Sorry. x1 is a coordinate of the fixed point. And because the coordinate of this fixed point satisfies this equation, and we use this fact in this reasoning. But this equation, x1, x1, this equation is the equation of the straight line. And in this equation, x is a variable, and x1 is fixed number. And we obtain that this equation and this equation has various sense. This equation, the equation of the curve on the second order, the quadratic equation, but this equation is the equation of the straight line and the equation of first order. And in this equation, x1 and x has the various sense. x1 is fixed, x is variable. And this formula is our goal. We try to obtain this formula. And when we obtain this formula, we obtain this equality, left side and right side. And right side is fixed. This is a number. Left side is the equation. And we use the fact, the fact that the coordinates of point P1, which are equal x1 and y1, are satisfy the equation of hyperbola. And this exactly equation of hyperbola. And we change this expression by this, a2, b2. And after this substitution, we obtain the formula for the straight line, which is tangent straight line. The equation of hyperbola satisfies coordinates of any point which lies on the hyperbola. And because we have the equality b square x1 square minus a square times y1 square is equal to this equation. And this equation, x and y, is not lies on the on the straight line. Is not lies. But the form for straight line is in some sense in the same as the equation for the straight line. But this x, oh, I'm sorry.
Yes, that's exactly
Yes,
what I'm
yes, my mistake. I don't understand your remark.
Yeah.
Mistake. Yes.
Yeah. Okay. Yeah, that's
Yes. But I finished. In this equation,
everything
x
is
and
clear.
xy are variables.
Yes. Yeah. Okay.
In this,
Yeah,
yes.
this was.
Yes. I don't understand your remark. Yes, it's the same. X1 and Y1.
Yeah.
Okay. Yes. But I'm finished. This equation is the equation of the straight line, and x1 are variables, various quantities. X is variable, x1 is fixed. But the form is the same as the form equation, but in this equation, x is a variable. Okay, let's maybe consider some first example. Let's consider one more assertion about about tangent straight line. I have point P1, which has coordinate x1, y1, and we have foci f and f prime. F and f prime. We have point of intersection, the tangent straight line, and axis OX and axis OX. And we have also P1F and F prime F, the angle, and N be point of intersection of the tangent straight line and axis OX, and the assertion is the following. The tangent straight line bisect the angle F prime P1F, bisect this angle. And we have the theorem 2, the tangent to the hyperbola at any point P1 bisect the angle between the focal radii of the point. Let alpha be the angle f prime P1n, and beta be the angle n P1f. And we can briefly formulate the assertion of this theorem. Alpha is equal beta. Alpha is equal beta, or the angle f prime P1n is equal angle n P1f to angle. These two angles are equal. This angle is equal to this. For the ellipse, we have the same assertion, but bisect this angle, bisect the normal to the ellipse in the point P1. But in the case of hyperbola, the same property has the tangent, which bisect the same angle in the case of hyperbola. We have two orthogonal cases for ellipse and hyperbola. I recall the picture for the ellipse. In the case of ellipse, the normal divided bisect the angle between focal radii, but in the case of hyperbola, the same property has the tangent straight line. The tangent straight line in the case of ellipse, and the normal straight line. Normal straight line is perpendicular to the tangent, and it has the same property. Okay, let's prove this theorem. Let's prove this theorem. Okay. The proof of this assertion the same as the case of ellipse. These two assertions, the proving of these two assertions are the same. And I recall that in the case of hyperbola, as the case of ellipse, we have two straight lines which are called directrices and which satisfy the equation x divided x divided x is equal a divided e. Yes, x divided e and x divided minus x equal minus a divided e, two directrices. And by the one of the properties of ellipse and hyperbola, ellipse and hyperbola and parabola can be defined by the following property: the ratio of the distances from the point, any point of this curve, to ellipse, or the ratio of foci radius to the distance to the directrices, is constant and equal eccentricity. By definition of the any of the conics, the general definition of any conics, any conic. And if we have any triangle which sides A and B, and if maybe A, B, C, CC1, let CC1 bisect the angle BCA, and we have the main property of bisectors, the ratio BC to CA is equal BC1 C1A is equal the ratio AB. We have the following property from elementary geometry, which property can be easily reduced from the cosine theorem. And we will use this property for proving that the fact that this tangent straight line bisect the angle between foci radii. We have the same idea as the previous case of the ellipse. Let's calculate. Let's calculate.
1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 + 1 +
let's calculate the ratio P1F to P1F prime. By definition, this ratio is equal the ratio between point n f we can we can prove that the ratio is equal to the ratio NF NF prime. We have that foci radio P1F is equal product eccentricity times the distance between P1 and directrix. Directrix, the points of the directrix satisfy the equation x is equal to the ratio E, where E is eccentricity. The point P1 has a coordinate x1, a1, and this distance exactly equal the difference x1 minus the ratio a minus a divided e. Let R be the point which lies of directrices, and this point is point of intersection, the perpendicular which pass from P1 to the directrices and directrix. And this distance exactly is equal E P1R, and P1R is the difference x1 minus the ratio AE. And easy to see that P1F is exactly equal EX1 minus A. The same way we obtain that the difference, that the second focal radius P1F prime is equal the same way the product E times P1 R1, where R1 is a point intersection of the perpendicular which pass through point P1 and perpendicular to directrices. Both directrices are parallel between this the same.
Sorry, Professor.
Yeah.
Where is N in the picture?
Mm-hmm.
Where is it? N.
N is the point of intersection, of the tangent straight line and the axis OX.
And you also have connected the tangent and F prime, right?
Tangent pass through P1 and tangent straight line to the point P1. Yes, exactly.
Yes, thank you.
Mm-hmm. And our goal to prove that this tangent straight line bisect the angle between focal radii, and we try use this property, and if we prove this equality, we prove the theorem, because by the main property of bisectors sufficiently prove this equality, and from this equality follows that the fact that this straight line is bisectors. And the same way we obtain that the second focal radius P1 f prime is equal E times x1 plus the ratio A and E. Okay, and the left side is equal. Left side is equal.
I'm sorry, Professor.
Yeah.
What is R here?
O.
R.
R be the point of intersection of the perpendicular to directrices, with these directrices. This point lies on one hand on directrix, and other hand to the perpendicular to this directrix.
Okay.
And R1 is the same point on other directrix. And I calculate this distance between this point and this point by the main property of hyperbola. This distance is equal to the ratio of this distance or by eccentricity. By definition. By definition. And we obtain that left side of our equality P1f prime is equal this ratio E x1 plus A divided minus A, I'm sorry, E x1 plus A, the left side. And the second step in our proof to calculate the distance n f1 and nf, and after them calculate the ratio in the right side. How to calculate? We can use this equation for the tangent. In this equation, we can put the value of y is equal 0. In this case, we obtain the coordinate of x of point n. Point n is a point which has the second coordinate equals 0. By definition, the point of intersection with axis OX is such point, then the second coordinate of this point is equal to 0, by definition of this point. And from this equation, we can deduce that this point x is defined by equation minus y1 is equal b square x1 a square y1 times x minus x1. And we obtain the following equality minus a square y 1 is equal b square x1 x minus b square x1 square. And we can obtain the following equality: b square x1 square minus a square y square, which is equal a square b square, is equal b square x1 x. And after them we obtain the following equality: x is equal the ratio b square x1 divided a square b square. We subtract b squared, obtain x1 divided a square Let's check our calculation. Okay, and after them we can calculate the distances between n and f and f prime.
I'm sorry, Professor. Shouldn't-
Maybe a mistake.
y1 should be squared, I think, in the second line, minus a2 y1 squared.
Okay, let's check. I transform this equation by the following way: b square.
No, the first line, Professor. The first
This right? This equation, right?
first line, the first line.
First line.
Minus, yes. My a squared times y1 and then times another y1 when we move on to the second line.
Yes, I multiply left and right side, and b square x1 x minus, that's right.
Yes, this y1 should be squared, shouldn't it?
Yes, thank you. Yes, okay, yes, you're right. That's after that, this right. Maybe that's right. Okay, let's finish our calculation and let's calculate nf and nf prime. Nf equal f has coordinate c0 and c is equal ea, and nf is equal ea minus x1 divided a square. Maybe a mistake. C X X1 X X1 divided A square. Maybe C. Excuse me. C1 yes, exactly. Yes, it's right. Maybe let's check. B square maybe mistake. X1 Y1 is equal A square okay. I'm sorry. I'm sorry, mistake in this one. Let's calculate x is equal the ratio a square b square divided b square x1. I'm sorry, b square. Subtract and we obtain a square divided x1. And the ratio is equal a squared divided x1. That's exact. And f prime, the same way, is equal ea plus a squared divided x1. And the ratio n f and f prime is equal e a minus and after simple transformation we obtain e a x1 minus a square divided e a x1 plus a square and equal e x1 minus a divided e x1 plus a. And we obtain the same ratio and f prime. And we finished the proof of this theorem, this mistake. We can change denominator, and obtain the right answer. Okay, we obtain the analog of the same property of the ellipse, but the role of normal straight line in the case of hyperbola plays the tangent plane the tangent. And in this both case we can the two properties which one be analogs of other. But in these two cases we change tangent and normal straight line. But the assertion is the same. This straight line bisect the same angle between foci already. Okay, and the last main theorem, which can prove the same way, the last theorem 3. This theorem about tangent to the general curve of the second order to the any conics. Theorem 3. Let we have arbitrary conic in any coordinate system. I recall that the general conics in general coordinate system has the following equation. The equation is a polynomial of the second order: a x squared plus 2bxy plus cy squared plus 2dx plus 2ey plus f is equal 0. Then the equation of the tangent in at the point P, which has coordinate x1, y1, can be written in the form a x1x plus b x1y y1x c y d x plus x1 plus e y plus y1 plus f is equal 0. Proof the same. I suggest to prove this theorem using by the same approach as the previous cases. And let's start and continue to the second part of our lecture, quadratic surfaces. What it means quadratic surface? We have three-dimensional space, and we can consider the polynomial of the second order, but which polynomial depends from the three independent variables x, y, and z. This variable be the coordinates of the arbitrary point in the three-dimensional space. And all points which coordinates satisfy this equation, the equation left side of which is a polynomial of the second order, is a we will call quadratic surface. We have the polynomial of the second order, hy twice iz plus g is equal 0. The general form of the quadratic surface. We also will use the other notation for the constant A, B, C, D, so on, using one letter A with indexes A1, 1, x1 plus A2, 2, y2 plus A3, 3, z square plus 2A1, 2, xy plus 2A1, 3, xz to A2, 3, yz plus 2 A1 x plus 2 A2 y plus 2 A3 z plus A0 is equal 1. We also use the notation. Let's introduce the matrix Q, which matrix 3 by 3, A1, 1, A1, 2, A1, 3, A1, 2, A2, 2, A2, 3, A1, 3, A2, 3, A3, 3. And we can use notation x, large letter x from the vector x, y, z, and we can use notation f for the vector A1, A2, A3. And then this equation can be written in the matrix form, using matrix formalism, in the following form. In the following form. Namely, x transpose qx plus fx plus a1 is equal 0. This part, or equivalently, this part is called quadratic part of this equation, quadratic. And this expression is also called quadratic form, This part is equal linear form. And our equation is a sum quadratic form and linear form. We can also use the extended matrix A, which has the following form. And we also use extended vector x bar x, y, z1. And then this equation can be written in the form x transpose A x is equal to 0. We have three equivalent formulas. 1, 1 prime, 2, 3. We have three equivalent equations for the quadratic surface. Using the same way, we can reduce this formula to the two following cases. Using rotation in the space and vector shifts, we can obtain the following equations for the quadratic surfaces in the form a prime x squared plus b prime y squared plus c prime z squared is equal to d prime, or in the form a prime x squared plus b prime y squared is equal to c prime z.
Sorry, Professor.
And this more simple form, yeah.
Xt means X transpose?
T, yes, T it means transpose matrix. Transpose mean when we write rows as columns and then inverse columns as rows in the matrix.
I see.
Yeah.
Yeah, thank you.
For example, x is equal x, y, z, 1 transpose. Yeah, this the theorem, very important theorem, which it asserts that any equation of such type can be written in this following form. We can construct such a reference system, a coordinate system, such that in this coordinate system, the equation of our quadratic surfaces can be written in this more simple form. We later prove a more general assertion, which true for the arbitrary quadratic form in the n-dimensional space. But in the case of surfaces, we can prove this assertion by the same way as we before proved the same theorem for Conics, using the rotation but rotation in the three-dimensional space. But this rotation can be reduced to the rotation for the rotation about coordinate axis, and such way we can reduce the arbitrary rotation to the rotation about coordinate line and to the two-dimensional rotation in the plane. Okay, let's consider some example of quadratic space. The first example is a sphere and cylinders. What does mean sphere? sphere is the three-dimensional counterpart of the circle. And let C be point with coordinate A, B, C in the space. Then the sphere is a set of the point which coordinates are satisfy the following equation. The sphere is a point in the space. For each of them, the distance between this point and some distinguished point C is constant. I recall that the coordinate of the vector, which the endpoint, the arbitrary point of sphere, and the other point, origin of this vector, is a C. And the distance is equal the length of these vectors. And the square of the length is the scalar square, or dot square of this vector, and can be defined as the sum of squares of coordinates of this vector. The coordinates, if this point M has coordinate x, y, z, then the vector C M has a coordinate x minus a, y minus b, z minus c. And dot product of this vector is defined by the formula the square of x minus a by y minus b square plus z minus c square. And this dot product is constant and is equal r square, r some constant. And this sense of this constant is the length of this vector. Exactly is the distance between arbitrary point of the sphere to the fixed point C, And this constant r is called radius of the sphere, And we obtain the following equation of the sphere is equal r square. If we have arbitrary equation in the form x square plus y square plus z square minus 2ax minus 2by minus 2cz plus d is equal 0. This equation can be written in this following form. And inverse, if we have the same equation in such form, we can use this equation to this following form. And this equation is the equation of the sphere in the arbitrary reference system, in the reference. I have any time, but I would like to say some words about.
Sorry, Professor.
Yes, the question.
Why do you multiply Cm times Cm?
CZ. This line.
I mean, why did you multiply two Cm's together, Cm times Cm?
Together C. C. Z minus.
Yeah, Professor. I mean, the line before that. This line in the middle.
In the middle.
Yeah. This Cm. Yeah. This line. Yes, this line. Why did you? The reason that you multiplied CM and CM?
I don't understand.
The left-hand side, Professor. Why are we
Left side.
multiplying CM? Yes. Why are we multiplying CM and CM? The two vectors are the why are we multiplying
C dot CM
times CM.
Yes, CM, yes. CM, yes. What's the question?
What is the reason of the multiplication?
What's the reason to the multiplication? Yes. By definition, the sphere is a set of the points which defined by the following property. The distance between of any point of this set to the some fixed point C is constant. What does mean distance? We can consider the vectors which have as endpoints C and M, vector Cm. I recall that the square of the length of this vector is exactly equal the dot square of this vector, and this is equal Cm square. The dot square is equal exactly the square of the length.
And what does the square of the length mean? Why is it? Why do we need it?
Why this equality?
No. I mean, why? What's the use? When do we use the square of the length? When do we use it? What is it used for?
I recall that if we have two vectors A and B, the dot product of this vector, by definition, is the product of the length of this vector and cosine of the angle between this vector. In this case, in the case when A equal B, we obtain A dot A, and is equal exactly the length of the A times, and we exactly obtain the square of the length. And if the vector A has coordinate x, y, z, the coordinate of these vectors, the A times A is equal x squared by y squared by z squared. I use only these two formulas.
Yes, thank you very much.
These formulas gives us, this formula gives us the first equality, this one and this one. And this formula gives us the two equality, this one and this one. And we obtain the equation of the sphere. As a result, we obtain the equation of the sphere using the definition of the sphere.
Thank you very much.
Do you understand, yes?
Yes, thank you.
Yes, I answer. Okay, and some words. If we have the equation of the some conics, but for example, we have the equation x squared by y squared is equal 1, the equation of the circle in the plane. Let me consider this equation in the space. In this case, virtually present the third coordinates z, but this coordinates absent in this equation. What does mean this fact? We have circle in the plane. And if we consider some point which lies on our circle with coordinates x, y, 0, and let's change the coordinate z and consider the arbitrary point, and consider the point which has the coordinate x, y, and arbitrary coordinate z. Z is absent in this equation. And if coordinates x and y satisfy this equation, with any point with the same coordinates x, y, and arbitrary coordinate z also satisfy this equation. And in the space, we obtain that if any point with coordinates x, y satisfies this equation, the point with coordinate x, y, and arbitrary z also satisfies this equation. And we obtain that if some point belongs our surface, the point with the same coordinates x, y, and arbitrary coordinate z also satisfies this equation. And we obtain the surface which calls cylinder. And any cylinders defined by the same equation as the equation of the conics. But this equation we consider in the three-dimensional space. And we obtain wide class of the surfaces which are called cylinders. And I haven't any time, and let's finish our lecture today, but next lecture I finish this term. And maybe in the next lecture we consider some tests on the previous materials which will be included these all themes. Without quadratic surfaces.